Hello, everyone. We're going to talk about the concept of invertibility. So we want to define what it is, and then the purpose of this video to see if we can apply it to various graphs and equations to determine are those graphs considered invertible. So the first thing I have here is we are going to try to define what it means to be invertible and some kind of quick ways that we can test to see whether or not it satisfies those conditions. So the overall definition of invertibility is that the original graph has to be a function, and the inverse, so after we transpose all of our x and y coordinates, if we graph the inverse, we need that to also be a function. So we can do this using two quick things. The vertical line test will tell me whether or not the original graph is a function. So I'm going to write that down here so you can refer back to it later. So a vertical line test determines whether a graph is or is not a function. And this should be something that you're familiar with. You've probably heard the phrase before, for every input, you can have only one output. And with that being said, what the vertical line test is if I were to draw a vertical line on my graph, anywhere on my graph, it's allowed to intersect with my curve at only one place, right? So in this case, this graph that I have on the left will be a function. It does pass the vertical line test. And now I can go to the next test to see if this is actually going to be invertible. All right, so let's get rid of these lines here. So the horizontal line test is going to determine, let's write this down, is going to determine whether the inverse graph is a function, right? Now, both of these tests must pass in order to be called invertible. So if I were to draw horizontal lines on my graph, anywhere on my graph, it should intersect my curve in only one location. And in this graph, it does, right? So I have this little curve over here on the left, and no matter where I draw a horizontal line, it will have only one point of intersection. So it passes the horizontal line test as well. So what we have here is if you have a graph that passes the vertical line test and the horizontal line test, that means both the original function and the inverse are functions or can be classified as functions, and thus we have something that is called invertible. Okay, so we're going to do this with a series of problems. I have a counter example here so you can kind of see it. So below is this graph that I have here now on the screen is got a little bit more extrema, so it has a maximum and min. It looks fairly cubic, but we want to know, is it invertible, right? That's the overall goal. So does it pass the vertical line test, right? So that's the first piece. If I were to draw vertical lines up and down on my graph, okay, and I can extend them all the way to the top and bottom, that's all right. Does each of these vertical lines only intersect at one location? And I believe it does. You know, I'm looking at the red curve, right? Where does the blue lines hit the red curve? And I think all vertical lines will hit it only one time. So this does pass, right? Now, for the horizontal line test, if I were to draw horizontal lines on my graph, so let's get a different color here. And I'll draw one right off the bat. If I draw a horizontal line right in the middle of my graph, you can clearly see that this horizontal line hits that red curve 3 different times. That is not acceptable in order to call something invertible. So what this says is this fails, okay? And the conclusion I can draw is that the inverse is not a function, okay? So since one passes and the other fails, the only conclusion that we can have here is this is not invertible, Okay, I'll say it once, I'll say it again, over and over. It must pass both line tests, vertical and horizontal, in order to be called an invertible function. Okay. Next series of problems are the parent functions. So the quadratic, cubic, quartic, so on. And if you look at these, now these are all functions. We know that these are the parent functions. They're all going to pass the vertical line test already. So we really only need to test the horizontal line test on these, right? So if you look at the quadratic and I draw a horizontal line, we can see that it's going to hit twice. That is not invertible. If I draw a horizontal line on the cubic, that intersects only one time. Now it looks like in the middle here at the origin, it kind of goes horizontal, but if I were to zoom in, if I had the technology to kind of zoom in, you would see that doesn't actually ever go specifically horizontal. It just decreases or in this case, increases at a very low rate. So this is invertible. Horizontal lines will only hit it at one place. With the quartic graph, the parent quartic, just like quadratic, they're very similar. They're not invertible. Quintic, so the fifth degree parent function, if I draw horizontal lines on that, okay, it will intersect at only one place. Again, at the origin, it's kind of the same thing as a cubic. It looks like it goes horizontal, but it really changes at a very, very slow rate there. So this is invertible. There are no places where a horizontal line would hit it more than one time. Sixth degree polynomial will hit it twice. That's no good. That's not invertible. And seventh, just like the cubic and the quintic, seventh degree polynomial intersects only one time, so that's invertible, right? So if you take a look at these, let's scroll back up. The second degree, fourth degree, sixth degree, all of these even degree polynomials, parent functions, are going to have that kind of parabola look. And that's going to make them fail the horizontal line test every time. Their end behavior kind of does not allow them to be invertible. However, the odd parent functions, third degree, fifth degree, seventh degree, they're all very, very similar. They will pass both horizontal and vertical line tests. So on the bottom here, as far as what conclusions can I make about the relationship between the degree of the function and the ability to be invertible, I can say that all odd degree parent functions are invertible. Now, there's a key word there, parent functions, right? All odd degree parent functions are invertible, but that does not mean all odd degree functions are invertible. We'll get into that in a minute. But likewise, we can say that all even degree, hang on, parent functions, and I can actually generalize this. Excuse me, my pen is having some difficulties. Let's try this again. Let's erase. All right. Even degree parent functions are not invertible. Okay, so again, odd degree parent functions are, even degree parent functions will not be, and then the odd degree only goes for the parent functions, not for all odd polynomial functions. Okay, so we have a few problems here. We're going to talk about, well, what happens if I restrict the domain, right? What if I talk about a piece of the graph rather than the whole, right? So we just described, this is the parent quadratic here, right? This is not invertible, right? We've already done that. It will not pass. It will not pass the horizontal line test. It will intersect more than one time. However, if you take a look at my part B, is the function f of x equals x squared where x is greater than or equal to 0. So if you look at this piece, I'm now restricting the domain. I'm saying I don't want to look at the whole graph. I just want to look at a chunk of it. So here is my original graph on the left. And I've kind of showed the progression of, I don't want to even look at the left side of it. I only want to know when x is greater than 0, and that would be everything to the right of 0. So that's where I'm at here. Now, if you look at that graph, just that chunk, is that piece invertible, right? Will that piece pass both the horizontal and vertical line test? And the answer would be yes. It would. The horizontal and vertical lines would only intersect one time. So this is invertible. Okay. All right. Now I have something that's got a little bit more substance to it. So here I have a cubic. It's a negative cubic. You can clearly has a absolute, or it has a relative min. It has a relative max. It has 3 x-intercepts. Right. We got a lot going on here. And I want to know, is the function invertible over the given intervals? So the first interval I have for part A here is when x is less than 0, right? So I'm going to try and use my highlighter on my screen. So when x is less than 0, let's see if I can do this. There we go. So when x is less than 0, I have this portion, everything to the left of the y-axis, right? That's going to be where x is less than 0. So I'm going to kind of make a little doodle down here. Ooh, I don't want to use my highlighter anymore. Let's change that. Okay, so if I make a little doodle of just that section, it looks something like this. Now, that has to pass both the horizontal and vertical line test still. Those never change. And if you look in this particular portion of my graph, that's going to intersect twice. That will not be invertible. So in this interval, I'm going to say no, it is not invertible when x is less than 0, right? So let's take a look at the next one, part B. What about when x is greater than 0, right? So let's get rid of this. And if I talk about when x is greater than 0, I'm going to talk about everything to the right. Okay, so this highlighted area, everything to the right of the y-axis. So if I look at that section of graph, right, I'm going to make a little doodle of what that looks like. Let's see what we can do here. And let me take a look. So it has a little y-intercept, goes up and comes down. So we have this piece of graph. Now, I think similar to part A, if I draw a horizontal line on this, this will not pass the horizontal line test. So again, is it invertible over that restricted domain, over just that chunk of graph? And the answer would be no. No matter where I draw that horizontal line, you're going to get 2 points of intersection. Okay, let's go to part C, right? So if I scroll up, let's erase this highlighting. Let's put some new highlighting on there. Part C asks for the interval from -1 to 1. So I'm going to start at -1 and follow my graph all the way until I get to the x value of 1. So between these two x values. So that's that graph. Now, if I doodle underneath here, let's see what that looks like. I like to separate it. So from -1 to 1 is kind of like this chunk. And if I draw any horizontal lines on that, it's going to hit my graph in only one place. So that's good. There's only one intersection for every horizontal line, and the same would be true for every vertical line. So in this case, this would be invertible, or that section of graph would be invertible because, like I said, the theme of this is that it passes both the horizontal and vertical line tests. Okay, so that's the last problem I have. Hopefully, just to summarize, you guys understand that in order to be invertible, a graph must pass both the horizontal and vertical line tests, right? A vertical line can only hit it one time or intersect with it one time. Horizontal line can intersect with your original graph only one time as well. So if you, hopefully this was helpful, and stay tuned for my next video.